Thursday. I can put it in the testing center. You can take it some other time. So if you got a good reason, don't worry. So we were talking about probability. And probability is a fraction between 0 and 1. It can be a decimal between 0 and 1, or it can be between 0 and 100%. And it's the ratio of the favorable outcomes to the total number of outcomes. And like, outcomes are either favorable or they're unfavorable. So we looked at some examples. So that's what we're going to do today, is we're just going to look at some more examples to get used to doing it. And I just realized this problem here we'd actually worked before. So the question was, if 2 dice are tossed, what are the probabilities that the following sums are obtained? We started this, so let's just go ahead and answer the remaining questions. What we did was we made up this table to show all the possibilities. There was no fundamental counting principle that we could use to come up with the number of occurrences for each case. So we basically just had to write everything out. We could answer the question using fundamental accounting principle to give us the total number of different arrangement or different choices, which is 36. There's 36 values here. But to answer specific questions, and I think, let's go back, I've already forgotten what the numbers were, 2, 4, 7, and 10. So let's, so what we'll do is add page here. So the question is, what is the probability of getting a sum of 2? What's the probability of getting a sum of 4? What's the probability of getting a sum of 7? And what's the probability of getting a sum of 10? So in all these cases, the denominator of the probability calculation is the total number of possibilities, what they call the number of elements in the sample set being here, all these 36 sums resulting from adding the 2 die together. So all we have to do is, with the denominator always being the same, which is 36, all we have to do is figure out what the numerator is. And to do that, we just have to count how many occurrences of each one of these things there are by going to the table. So if we look at 2, you see there's 1, 2 right there. If we look at 4, there are 3 4s. And if we do 7, there's 1, 2, 3, 4, 5, 6. So there's 6 number 7s, and there are 3 number 10s. So those are the probabilities of each one. And if we took the probability of getting a 2 or 3 or 4 or 5 or a 6 or a 7 or an 8 or a 9 or a 10 or 11 or 12, you add this together, you get 1, because we're going to get one of these possibilities. And then you can, in this case, we can't simplify any further, but these we could simplify the fraction by dividing by a common factor. And so we would simplify it if possible. So those are the probabilities. So the sum that has the highest probability ends up being 7, number 7, which has a probability of 1/6. So if you roll a die 1 out of every 6 times, you'll get the sum of 7. Okay, so let's go to another one. And I think we talked about odds, didn't we? We introduced odds. Yeah, so let's just cover that again. So the odds, again, this is in your book. If all outcomes in a sample space are equally likely, A of them are favorable to the event E, and the remaining B outcomes are unfavorable to E, then the odds in favor are A to B, and the odds against are B to A. Okay, it's okay. It doesn't matter who what is. Just try not to be distracting to the other class people. What's that? Oh, did I? Is that what I did? So there's also converting between probability and odds. Again, this is in your book. So if the probability is defined as the number of, you have to be careful here because the A's and B's and the different definitions are different. So in the previous one, A in the odds definition, which is over here, A was the number of favorable outcomes and B was the number of unfavorable outcomes. But here, A is the number of favorable outcomes and B is the total number of outcomes. So what they're saying is if you know the fraction that represents the probability to find the odds, all you have to do, the odds in favor of event A, all you have to do is say it's A to the denominator B minus the numerator A. So as an example, if I knew that the probability of something, of event E, was equal to 5/7, then the odds would be 5 to 7 minus 5, or 5, we wouldn't write it as this, we'd do the math, so it would be 5 to 2, favorable to unfavorable. Because what we have is we have 5 favorable, we have 2 unfavorable for a total of 7. So that's how you do the calculation from probability to odds, and then you can do it the other way. So let's say the odds, and this is odds in favor, meaning it's supporting what the event E is. Let's say the odds were 5 to 7. What is the probability of in favor? The probability in favor, what you do is you take 5, which is the favorable outcomes, and you divide by the number of favorable outcomes plus the number of unfavorable outcomes, which is the total number of outcomes, and so you would get 5/12. So the odds 5 to 7 is the same as the probability of 5 over 12. And if you wanted to find the odds against, it would be here in this particular example, the odds against this event occurring would be 2 to 5. So you just switch the two numbers. To go for odds 4 to odds against, you just switch the two numbers. Because when it's against what's favorable becomes unfavorable, what is unfavorable becomes favorable, so that's why they just get, pardon me? Yeah. Yeah, I mean that's a little bit different because they're not, what is, so I think what it is there, it's different than the odds we're talking about here. Yeah, because you could still use that, but it's not, I don't think it's the way that odds are used. I think what it is with something like that is if you had, let's say it's 3 to 2, you would have 5 games. One team would win 3 of the games and another team would win 2 of the games, kind of thing. But that's, which I guess is something, I mean, I guess that could be the same thing. Yeah, well, maybe it is the same thing because it's if you're, whatever the first team is, the one that, the 3 to 2, it's 3 favorable and 2 unfavorable, so I guess maybe it is the same thing. Yeah. Yeah, I had the same question, so that's good. Okay. So let's just do a few examples of, so this is probably a problem in the book. I'm not sure which one it is, but if anybody wants to find it, I'll find it so you don't have to write the problem up. I think I did bring my book. Yeah, there it is. So this is chapter 11. So what they're asking for here is they want you to find the odds against each result and the probability for each result. And I think the easiest way to do those problems is to just do the probability for first, and then we could do the odds for, and then we could just switch them to find the odds against. and instead of trying to think too deeply. So this is problem number 10 in the book. So I think that's what I'm going to use here. So we're going to do A. So the probability of picking Kathy, that's what we're doing. So the favorable event is picking Kathy. And you say, okay, well, how many possibilities do I have? If we go back to our definition of probability, way back here, it says the number of favorable outcomes, which is picking Kathy, divided by the total number of outcomes. Well, the total number of outcomes in this case is the total number of people to choose from. So the probability for picking Kathy is 1 picking Kathy divided by 5, the 5 remaining people. So this is the probability for picking Kathy. So the odds for are going to be 1, 2, 4, because the number of favorable outcomes is 1. Unfavorable is picking Alan, Bill, David, or Evelyn. So the odds against are you just switch the two. So it's 4 to 1. Okay, so next we do the probability of picking a woman. So then you look in how many women do we have out of the 5 people. The denominator is going to be the same, just like it was for the previous problem. So how many women do we have? 2. Yep. So that's the probability of picking a woman. The odds for are going to be 2 to 3. So the odds against are 3 to 2. And then the last one, once you guys do that and online. So what I'm going to ask you to do is, for people online, is to put the odds against. So this last number, you don't have to, if you get that right, then I know you've done the rest right. So the denominator is still 5. Hopefully you remember what consonants are. Is that right? Okay. They're going to have a new class in a year or so, not next year, but the year after. Well, they are going to offer it over in Rockbridge. But they're switching from the current format of 151, 152. The first semester is going to be called quantitative reasoning. And it's going to be similar to some of the topics that we cover in first semester in 151, but it's going to be less topics but more detail. And the second semester is going to be statistical reasoning. So it's going to just do statistics. I don't know if it's going to talk about probability or not. They say it's going to be descriptive statistics, which we're going to talk about that as well, but we're not going to spend the whole semester. So they're going to have those two options. And the reason they did that is they had this committee that met with representatives of 4-year colleges and said, what do you guys, what's the most transferable credit for you? And typically people who take math for the liberal arts, their degrees, they take at least one, they take one math class usually. And it's usually called quantitative reasoning for some. Pardon me? Sounds complicated? It's just, yeah, it's a fancy name for, it's supposed to be just problem solving and thinking about numbers. And Yeah, yeah. And oh, the reason I was bringing this up, I was like, where am I going with this? But I do remember why I started. Part of the quantitative reasoning class is a writing assignment. So we'll have to do a writing assignment for math. And I said, well, what are they going to do as a math assignment for writing? And they, Tondalea Van Leer, she said, well, we already do that. We do like double negatives. And I go, oh, give me a break. Well, yeah, but that's pretty weak. Okay, let's see if anybody's got the answer here online. So the odds against are 2 to 3 according to Harmony. So let's see. How many people agree with that? Okay. So what you have is persons whose name begins with a consonant. So it's B, C, and D. There are 3. So the probability for picking a person's name with a consonant is 3 over 5. The odds for are 3 to 2, and the odds against are 2 to 3. So that, I think Harmony got it right. By the way, does anybody know that they're not going to be here Thursday besides Tanner's pretending to be sick? Yeah, you have your class after this, so we'll have to figure out what to do. So what I may do is give you the test to take right away. Because you leave, what time do you leave? So if you come a few minutes early, no, I'd rather you take it on Thursday. Okay, let's move on to something different. You know, these to me seem very simple, but hopefully they are to you as well. So this is problem 14. In a hybrid corn research project, 200 seeds were planted, 175 of them germinated. Find the empirical probability that any particular seed of this type will germinate. So what they're doing is they're using, in this case, they're using inductive reasoning to come up with a probability, and then once they have that probability, then they can use that to say, if we pick any seed now, the next seed that I check, what's the probability of that seed being germinated? So it's going using the reasoning one direction and then going the other direction. So to answer the question here, to calculate the empirical probability, all we have to do is, again, take the ratio of the favorable events and the favorable event. So we just have to read this and figure out what's the favorable event. What is the favorable event, Tucker? What's the favorable event in this problem? Yeah, so the favorable event is germinate. So the probability of germinating is the number of times it germinates divided by the total number of seeds that were planted. And in this case, we simplify it down, and you can divide the numerator and the denominator by 25 to get the simplified result. So the probability is 7/8. They don't ask us, but the odds for germination would be 7 to 1. So we do the odds on the simplified fraction. I mean, I guess you could say it's 175 to 25, but that would be much harder to, 7 to 1 is much easier to understand. So that's the empirical probability, 7 over 8. And so what they're saying is now this is, and we've planted a lot of seeds, so the law of large numbers says that our empirical probability is close to the theoretical probability. I mean, the theoretical is, what does theoretical probability mean? It just means that whatever mechanisms cause the seed to germinate or not to germinate, there's some, it's just like radioactive decay. It happens because of physical reasons, and there's physical reasons for that to happen. So you could call it theoretical. It's not something you can predict by using an equation, but it's still, once you run enough experiments, then the empirical result approaches the theoretical result. And the question, if you take the other kind of statistics, well, I guess it's statistics. If you were designing, if you were a scientist and you wanted to know how many seeds do I need to plant to get a reasonable estimate of the theoretical results, that's a question you have to use inferential statistics. There is a certain number of experiments that you have to run to know that you have a reasonably good probability of the result being accurate within a range of numbers. Okay, so that was pretty easy. All you had to do, the hardest part was simplifying the fraction. Okay, probability of 2 daughters among 4 children. It says in example 3, would Kathy's probability having exactly, what would Kathy's probability of having exactly 2 daughters if she were to have 4 children altogether? You may want to use a tree diagram to construct the sample space. So you could, there's 2 ways you could solve this problem. What we're doing is we're assuming that the probability of having a boy or a girl is 50%. So it's like flipping a coin. So we could use this tree diagram just like we use the tree diagram for flipping coins, or we could use that thing we learned just recently, the combinations things, because it is like flipping a coin. I mean, obviously getting pregnant is not like flipping a coin, but it could be, maybe, I don't know. So I'm going to use the other way instead of doing a tree diagram. So remember what we said, if you could do you would have, these are the possibilities: no girls, exactly 1 girl, 2 girls, 3 girls, and 4 girls. So those are the 5 possibilities. And so the number of arrangements, if you want to call them, for each one of these would be taking 4 things 0 at a time, 4 things 1 at a time, this combination, 4 things 2 at a time, 4 things 3 at a time, and 4 things 4 at a time. So the first and last are always 1. The next to last are always the same number that you're choosing from. And you can kind of think back to Pascal's triangle, where, and then the middle number ends up being a 6. And you could, the long way, let's just verify that we're doing this correctly. So remember, the formula says it's 4 factorial divided by 2 factorial divided by 4 minus 2 quantity factorial. So let's see, what do we get? 4 factorial is 4 times 3 times 2 factorial. The denominator is 2 factorial times 2 factorial. So you cancel those out. We're still left with 2 factorial in the denominator. And you see I get 6. So it is, I did do it correctly. So those are the 5 different possibilities. No girls means you'd have a boy, a boy, a boy, a boy, and then you'd go insane. I don't know what happens with 4 girls. You probably still go insane, just not as much. They always say, well, I've had 3 girls already, so it's time for me to, what would be the words? They would say, it's probably a better chance that I'm going to have a girl this time. The reality is that it's always about 50-50, unless there are some, there are some biological reasons that people have more boys than girls or more girls than boys, but in general, it's just You don't get more likely to have something because you've had something before. Anyway, if we add all those numbers together, we'll get 16. And then remember that we know what the total number would be because we have 4 things happening: having a child, having a child, having a child, having a child. And there are 2 choices each time, boy or girl. So you take 2 to the 4th power, 2 times 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 2. That gives you 16. But those are all the different ones. So so now we can answer the question. We know the total number of possibilities are 16, and exactly 2 girls is 6. So answering the probability questions, once you've done the counting part, is pretty easy. Sometimes just counting. So the probability of getting exactly 2 girls, which is the same as getting exactly 2 boys, is equal to 6 divided by 16, which we would simplify that down to 3/8. And the odds for 2 girls would be 3 to 5. And the odds against would be 5 to 3. I mean, the most likely situation is to have 2 boys and 2 girls. So how many people, I'll ask the women in this group, the 2 of you have had children, does the wives' tale, I don't know if it's a wives' tale or not, that if you have a more difficult pregnancy, it's going to be a boy, and if it's an easier pregnancy, it's a girl? So true, yeah. The question is, is it actually true or not? I don't know if it's true or not. My wife believes it, even though it got shot down with Heather because she had a pretty good pregnancy and she had a boy. So. Is it that high? Yeah. Okay. So the next one is a genetics question. Suppose a child is born with 1 cystic fibrosis carrier parent and 1 non-carrier parent. Find the probability of each of the following events. The child will have cystic fibrosis. The child will be a healthy cystic fibrosis carrier, and the child will neither have nor carry the disease. Do you remember genetics from your high school biology class? Possibly. Does anybody have any relatives that have cystic fibrosis? Does anybody know if they are carrying the cystic fibrosis gene as a recessive gene? Oh, really? Yeah. Both of my daughters have the carrier gene, so either I'm a carrier or my wife's a carrier. We don't know because we haven't had the genetic testing from our perspective, but I don't know of anybody who had cystic fibrosis, but it could be a couple of generations back and they died. They didn't say what they died of, so you don't really know because you can go through many generations as being a carrier before you have somebody. So what they do, just so if you're interested, which I'm going to tell you anyway, when this was Jennifer, the older daughter, so what she had, she was pregnant with twins, and she was 31, 30, something like that, 31. So she was beyond the age where you start to worry about Down syndrome and other genetic things. So they do a genetic test, and so I came back and found out that she was a carrier for cystic fibrosis. And so then what they do is they check the husband. And if the husband is not a carrier, then you don't have anything to worry about. And then since Jennifer was a carrier, they checked Heather, even though she wasn't as old when she got pregnant. So I'm not sure if they would have done the genetic testing if her sister hadn't had it and she was a carrier as well. But luckily they married non-carriers, so at least for her, the children they're having, but their children will, probably get, if they decide to have children, to get that checked. So, I mean, by the time they're having children, probably they'll do genetic testing for all kinds of different reasons besides cystic fibrosis. But and that's kind of the only way you find out these days is if you have somebody who's pregnant and they check for genetic. I want to use the right word there. Genetic issues. Okay, so all we have to do to answer these questions in terms of probability is think about how this genetics thing works. And the way it works is like this, is you have two parents. So we're not cloning yet. So so let's say this way is the mother and this way is the father. And if you're a carrier of the gene, you have a dominant gene and you have a recessive gene. So I'm going to assume this assumes that the mother has the carrier, and so it says one cystic fibrosis carrier parent and one non-carrier parent. So if this person has so this person has just the dominant gene, which is the non-cystic fibrosis. And what I'll do is I'm going to answer not just this question, but what if both parents have? We'll talk about that in just a second. But for right now, let's follow the problem as stated. So the chances of getting a particular gene from your parents is a 50-50 proposition. So the four different possibilities is to get the dominant gene from both parents, to get the dominant gene from the mother, but the recessive gene from the other way, father. Actually, the father has the defective gene. Okay, then you've got, so it's just like the table we did with dice. Instead of numbers, we put down the different arrangements. So this is the case where one is recessive and one has no. If we go down here, if you have, if both parents have recessive genes, then it looks like this. So you get recessive, dominant, you get dominant, recessive, dominant, two recessives. And this is the one you have to worry about, is where you get both recessive genes. Now you could have somebody who has cystic fibrosis, which, then your probability of having a child that has, if you married somebody who's not a carrier or a carrier, the probabilities change considerably depending upon what's going on with the parents. So in all these cases, there are four possibilities. So these are one recessive parent and one non-carrier parent. So all we have to do is figure out what the numerator is. So this will say will. Okay, the probability that the child will have cystic fibrosis. Well, you have to have both recessive genes. So in this case, there are 0 of these combinations that have 2 recessive genes out of 4. So the probability in this situation is 0, which is what happened with my daughters, except it was the mother who had the recessive gene. The probability of being a carrier, healthy but carrier, that's when you have one dominant gene and one recessive gene. So you look and you see there's 2 cases where they are healthy but have the recessive gene. So it's 1/2. And in the case of, we'll just say healthy, that's the case where they're not a carrier. This is where you have 2 dominant genes, so you get 2 divided by 4 possibilities, and you get 1/2. So my grandchildren have a 50% or 1/2 probability of being a carrier, and a probability of 1/2 of being not a carrier. Now, if you have the case here where you have 2 parents that have a recessive gene, but they don't have cystic fibrosis, in that case, the probability of having this cystic fibrosis is 1/4, because there's one case out of the 4 that they have 2 recessive genes. There's the probability of being a carrier is 2. There's 2 cases there, so it's 2/4 or 1/2. And the probability of being healthy without being a carrier is 1/4. So the question as a parent of a unborn baby is, what do you do? Now, I guess it depends on whether you can get a genetic sample from the child or whether you can get a sample from the amniotic fluid, which would tell you whether the child has. So it wouldn't be, I mean, the probability of getting pregnant and having, the question is, what do you do at that? You know, that's a moral, ethical dilemma of what you do. Luckily, we didn't have to face that, or my children didn't have to face it. Okay, the last problem in this section is, again, just it's not a counting problem. It's kind of a geometry problem, and it says, what is the probability? It says if a dart hits the square target, meaning this big square target there, what is the probability that it will hit in the colored region? So we have there's no aim here. It's just randomly gets placed within the target. The blue colored region. So all you have to do is think about, well, what is the total amount of, what's the sample space? Well, the sample space is the target. We're at least going to hit the target. The probability of hitting the blue is dependent upon the area of the blue shaded part. So how do you calculate the area of the blue shaded part? Well, what you can do is, we did this in the last semester, is we could find the area of this square, and we could subtract the area of this square, which would leave us this outside area, and then we could add back in the area of the center part. And that would give us the net area that's shaded. So let's just do that calculation. So what I'm going to say is, in this case, we're not counting, but we're calculating an area. So I'm going to say the equivalent of the size of the sample space is going to be equal to the area of the outside square. So that's going to be 8 centimeters times 8 centimeters, which is 64 centimeters squared. So that's this total area. In terms of the equivalent of counting the event is hitting the blue. So what I will do is I will take 6 centimeters times 6 centimeters. That gives me this area, all with everything included. I'll subtract 4 centimeters times 4 centimeters, which will give me, will cut out this area. So I just have this outside blue part, and then I add back in the area of the blue in the middle. So it's using subtraction and addition. So what do we get? We get 36 minus 16 plus 4, which is 24. 36 minus 16 is 20. 20 plus 4 is 24. So the probability of getting in the blue, which is the event, the favorable event, is just going to be 24 centimeters squared divided by 64 centimeters squared, which can be simplified down to, let's see, we can divide by 6. Let's see what happens. Divide by 6, we'll get 4 over, no, you can't divide 64 by 6, can you? So we'll divide by 2. 12 over 32. Okay, that's the centimeters squared cancel out. I can go a little further, so that'd be 6 over 16 or 3 over 8. Okay, so the probability is 3 over 8. So again, if I hit the target 8 times, 3 of those times on average in the long run will be in the blue area and 5 will be in the white area. Yeah, skill plays 0 role. Yeah, no, you'd have to, I don't even know if you could have an automatic dart throwing. You'd almost have to do it like in a computer, some kind of computer arrangement. So this is due next Tuesday. Just seeing who else is here today. Austin, Adriana, Josh, okay. Let me do a roll while. Before I forget about it. I'll put it back up in a second, don't worry. Okay, Tuesday, Thursday, 30th, 31st. Okay, Eli's here, or at least he was here. Taylor, Tucker, Adriana, Mary, Melissa. Is it Mary or Melissa? Oh, okay. Where did I get Mary from? I was thinking, I think I have, yeah, I have a Mary somewhere. Melissa, Tanner, Kristen, Josh, James, Austin. Okay. Okay, so there they are. I did get, I think I told you guys last semester, I did that genetic testing for genealogy sakes last semester. And I mean, I knew what it was going to be because I followed my genealogy back to not super far, but back to like early 1800s. And they're all from England, so it's not like it was a big surprise, but it was something like 40% British Isles, 25% Northern Europe, 15% Irish, a small percentage of like Spain and Portugal area, the Iberian Peninsula as they call it, and no Scandinavians. I have no Norse blood in my family, which is interesting because a lot of the sons, Peterson, Nicholson, whatever, that's kind of a Norse, like a Scandinavian thing. So I was expecting some Scandinavian, but there was no Scandinavian. But supposedly you can take that. I thought that if you did that, you could have like download the data and then you could send it to somebody else and they would do genetic, they could do genetic testing on you for what is it? Predilection. What's the word? I forget the word. What's that? Yeah, is that a word? Yeah, I mean, it basically means that you have a tendency towards something, which is what people worry about in terms of health. If you have genetic things that predisposition, that's what it is. Yeah. Okay. So the next section is events involving not and or. We just finished with that in chapter 10. It was the last section. It was the title was counting problems involving not and or. So this is events involving not and or. So it's not really that much different. It's just saying that sometimes it's easier to figure out the probability for the opposite of something happening than the probability for something happening. So if you can calculate what does that relate to as far as probability is concerned? So this is it kind of relates to this. These are properties of probability. And I've mentioned some of these, but this is a formal. So it says let E be an event within the sample space S. That's what we've been doing. That is, E is a subset of S. So for example, you know, the genetics, having cystic fibrosis is a subset of the other choices, not getting it or being a carrier. And if this is true, then the following properties hold. The probability has to be somewhere between 0 and 1. 0 means that it can't happen. Probability of 1 means it always happens. So the probability of me dying is 1. Okay, probability of anybody here dying. That's a certain event. We don't have to worry about that. The probability of us being born is 100% because we're here. But and then you have stuff in between. But probability is a fraction between 0 and 1. It can equal 0, it can equal 1, or it can be anywhere in between. So yeah, so this is just the word representation of what this says. The probability of an event is a number from 0 to 1, inclusive, meaning that means it can be either 0 in it, or it could be 1, or anywhere in between. The probability of an impossible event is 0. The probability of me living forever is 0. Okay, and the probability, so use this 0 with a line through it, which means in set theory means the null set. That means, so the probability of something not happening is, the probability of something never happening is 0. And S probably means something like certain, I would guess, or maybe it means the sample space. I don't know what it means. But so that the probability of a certain event, certain wouldn't be using S, though that starts with a C. So it probably means sample space. So what we're talking about here when we talk about nots or ors is, well, mostly not, is the probability of the complement. So the probability of an event, the probability that an event will not occur is equal to 1 minus the probability that it will occur. And you can write that in equation form as this. So that's the probability equivalent of the complements principle that we used when counting stuff. When we did counting, we said the total number of ways of something not happening is equal to the total number of ways minus the total number of ways something happening. In probability, we just say the probability of an event not happening is equal to 1 minus the probability of the event happening. And again, it's all because probability deals with things either happening or not happening. It's not measuring the temperature. So if you thought, you know, what's the probability of the temperature being 72 degrees? You would never ask that question. You'd say, what's the probability of the temperature being less than 72 degrees? Or what's the probability of the temperature being greater than 72 degrees? Greater than or equal to 72 degrees. You'll never see a probability associated with a specific event that it has multiple values. You could say, what's the probability? Well, I guess you could say, what's the probability of being 72 or not 72? But being exactly 72, that never happens either. It's never exactly 72 in the real world. So relating to this, actually I think this has more to do with, well, let's just read it. Mutually exclusive events. Two events A and B are mutually exclusive events if they have no outcomes in common. Mutually exclusive events cannot occur simultaneously. Yeah, I think we had something similar to that when we were talking about counting, or was it in sets? I can't remember. I think it was in the last section. Well, in the last section of chapter 10. Let me look in there, and I'll read what it said there. Okay, we got the complements counting, principal counting. Yeah, I think it was to do with when two sets were disjointed, meaning that the number of elements of event A occurring, they couldn't both happen together. I know we talked about it in set theory. So I think I'm using this example as say you have 52 cards, and you can look at the probability that you pick a heart or the probability that you don't pick a heart. And I think these would be considered to be mutually exclusive events, because you can't pick a heart at the same time as not picking a heart if you're just talking about one particular event. So let's look at the, while we're just talking about this, what is the probability of picking a heart based on what we know at this point? So the probability of picking a heart out of a 52 card deck is going to be equal to, well, the denominator is going to be 52. That's the total number of cards that I have. And the number of hearts is going to be 13, because there are 13 cards in a suit. And that simplifies down to 1 over 4. So the probability of picking a heart is 1 over 4. The probability of not picking a heart, there's two ways you could think about that. Well, there are, so one way would be to say, well, all the other cards are, which are diamonds, spades, clubs, there's 13 of those per suit, and then you times 3, you get 39 over 52, which simplifies down to 3/4. Or, using this complements principle probability, you could also say the probability of not picking a heart is equal to 1 minus the probability of picking a heart. And that's because these are mutually exclusive things. So you get 1 minus 1/4, which is 3/4. You get the same answer either way. So you just pick whichever, you pick whichever means is the easiest to do. If it's easy just to count the numbers and come up with the probability, that's fine. If it's easier to figure out a smaller number that relates to the complement, then you can use that. But all we're doing is just the same thing that we did before. And then we have this addition rule of probability. It looks very similar to the rule that we use for counting. But it says that if A and B are any two events, then the probability of event A or event B happening is equal to the probability of event A happening plus the probability of event B happening minus the probability of event A and B happening. And the result ultimately has to be between 0 and 1. I mean, it doesn't matter what the probability, how we define, how we come up with the probability. The probability number always has to be less than or equal to 1 and greater than 0. But again, we usually do this talking about things like cards. What's the probability of getting a something or a something, whatever, two different cards, and we can look at the probability of each thing occurring and then subtract the probability of them both occurring, and then coming up with the final answer. I heard a little ding. I don't know if there was a question. Oh, it's Austin skipping out. Okay. We'll see if he comes back or not. Okay, so that's pretty much it for this section. So let's just look at some problems. For the experiment of drawing a single card from a standard 52 card deck, find the probability and the odds in favor of each event. So we're looking at what is the probability of not picking an ace. So this is where you would use this, whatever they called it, where is it called? Probability of the complement. So I'm going to put this on a new page here. So the probability of not an ace is equal to 1 minus the probability of picking an ace. So the probability of picking an ace is the number of aces in a pack of cards, which is 4, divided by the total number of cards, which is 52. And you can simplify that, and you get 1/13. So if you divide both of those by 4, you get 1/13. So the probability of picking not an ace is going to be 1 minus 1/13, which is 12/13. So that's the probability. And odds in favor, you take the numerator and you say the numerator to this difference between the two. So it's 12-1. The odds in favor are 12-1. So that means if you did this experiment 13 times, over the long run, 12 out of the 13 times you would have, 12 times you would have not an ace, and 1 time you would have an ace. And this, whether it's an ace or a jack or a king, you'd have the same calculation. Okay, so here we have the king or queen. So this is the second part. So this is using the second bit because it's an or statement. So the probability of a king or a queen is the probability of picking a king plus the probability of picking a queen minus the probability of picking a king and a queen at the same time. So in this case, you can't pick a card and it be both a king and a queen. You can pick a 2. A 2 could be a spade, it could be any one of the 4 suits. But in this case, these are different, whatever you call those things, different cards. It's not very descriptive, but so in this case, to find king or queen, all we do is we add the probabilities of picking a king plus the probability of picking a queen and subtract 0, because this is 0. So the probability of picking a king, there are 4 kings out of 52 cards. And the probability of picking a queen, there are 4 cards out of 52 cards. And there are no cards that are both the king and the queen at the same time. So you add those 2 together, you get 8/52, which is, if you divide by 4, you'll get 2/13. It's twice what I got up here. So that's the probability. The odds for are 2/11. So that's pretty easy. And this is a kind of problem that I would put on the test to test you on your knowledge of using the stuff in this particular chapter. Okay, so here we go. Again, you can't be both a club and a heart at the same time. So these are just like the previous one. The difference is the probabilities of the individual events are going to be different because there are more hearts than there are kings or more than queens. So the probability of getting a club or a heart is going to be the probability of picking a club plus the probability of picking a heart minus the probability of a card that's both a club and a heart, which can't happen. So we get there are 13 clubs out of 52 cards. There are 13 hearts out of 52 cards. There are 0 club heart cards. So you get 26 over 52, which is a half. So the probability of picking a club or a heart is 1/2, and the odds for are 1 to 1. Okay, and the last one is where you have some overlap between the two. So you can a spade can be a face card, or it can be a non-face card. So we'll do this one. So the probability of being a spade or face card. So you take the probability of being a spade plus the probability of being a face card minus the probability of being a spade and face card. So the probability of being a spade is 13 out of 52 because there are 13 spades. The probability of being a face card, there are 12 face cards. That's king, queen, jack, 3 times 4 suits. So you get 52. And then you subtract the number of spade face cards, which are 3. 3 out of 52. There's this jack of spades, the queen of spades, and the king of spades. And so your answer is 22 divided by 52, which is 11 divided by 26. And the odds for are 11 to 15. So that's how those problems work. We're using, the first problem we use the complement principle of probability, and then the remaining 3. So anytime you see the word not, you should think, oh, I should use the complement. If I see the word or, then I should use the, what the heck did they call that? You just use those formulas that you need to know, if there are cases where you have both of them happening. What was it called? The addition rule of probability. Okay, let's skip all over that. So you can see there's not a whole lot left, so I'm going to go ahead and assign section 2 as well. So we'll just, what we do is on Thursday, the first 20 minutes we'll probably cover what we haven't covered today. We'll be finished with section 2, and then I'll give you the test. You'll have 50 minutes. But if you need additional time beyond that, I don't think anybody is in here after me, so you'll be able to have more time if you need it. You'll be able to bring a cheat sheet with anything you want to write on it, and you can use your calculator, but you need to make sure that you know how to do the factorial calculations. So, and you'll see it in the review if you watch it, but if I had something like this, or that's probably 5 things taken 3 at a time. What I'm looking for is you to actually write this out and do it so you wouldn't have to have factorial if you didn't have it on your calculator. Not everybody's calculator has factorial. So make sure you know how to do it the long way. Show all your work. So you guys, Harmony and Adriana and Josh, you're going to be able to be here and take the test on Thursday? Thank you. We'll see you then.